Section 7.2, Calculus of Parametric Equations. If you thought we were just going to leave this with parametric equations in the last section, that would be a strange thing for a calculus class. So we're going to recreate a lot of the things, the standard things that we've done, but just use parametric equations. So our first theorem is the derivative of parametric equations. Consider the plane curve defined by the parametric equations x and y in terms of t. Suppose that the individual derivatives, x prime of t and y prime of t, now these are with respect to t, the derivative with respect to t. Suppose those exist, and the derivative of x is not 0. Then the derivative dy dx is given by this equation right here. Dy dx is dy over dt, so the derivative with y with respect to t, divided by the derivative of x with respect to t, which is that y prime over x prime. Now you can sort of view this as the differentials, the dt's canceling, but that's not exactly what's happening, but that is one way to sort of remember what's going on there. Alright, calculate the derivative dy dx for each of the following parametrically defined plane curves. And then we're going to look for critical points on the graphs. I'm going to try to keep that graph hidden for the time being. Well, from what we have just seen, dy dx is the derivative of y divided by the derivative of x. So the derivative of y is 2. The derivative of x is 2t. And so that will be 1 over t. All right, now our critical points are going to occur. Critical points are going to occur whenever t equals 0 because it is undefined. Well, if t is 0, the point for that, evaluating each of those, is -3 and -1. So at -3, -1 is where we're going to have a critical point on our graph. So here is the graph in very small font. And here's our point, -3, -1. If you notice, the slope of that is undefined. So we can find that. And that is the only critical point here. And if you notice, this graph is actually not a function. That's one thing about parametric equations. We can actually have equations and do calculus with functions that do not have, that aren't functions at all. All right, so part B, again, dy dx is the derivative of y with respect to t, which is 3t squared minus 3, over dx dt, the derivative of x with respect to t, so that is 2. Now where that's going to be 0, this is not going to be undefined at any point, but where that's going to be 0 is when 3t squared minus 3 equals 0. Factoring out of 3, t squared minus 1 equals 0, which means t is plus or minus 1. Alright, so our t being equal to -1 and our t being equal to +1 are going to produce 2 points. Evaluating at -1, we have a -1 for x, and evaluating at -1 is 6. -1, 6 is our first critical point. Evaluating at 1, we get a point of 3, comma, evaluating at 1, 1 minus 3 plus 4, that should be +2, so 3, 2. There are our critical points, and checking that with our graph, we see the point -1, 6 is a local maximum. Okay, absolutely an extrema, an absolute, not quite absolute, but it's absolutely a local extrema. And the point 3, 2, same concept, we have a local minimum there. Alright, 1c. X of t is 5 cosine t and y of t is 5 sine t from 0 to 2 pi. Okay. So let's go ahead and find dy dx. The derivative of y with respect to t would be 5 cosine t. Derivative of x with respect to t will be 5 negative 5 sine t. Now, where are we going to have critical points here? Well, wherever 5 cosine t is equal to 0, or wherever negative 5 sine t is equal to 0, because this would be undefined. Well, cosine is 0 at pi over 2 and 3 pi over 2. And sine is 0 at 0, pi, and 2 pi in the interval 0 to 2 pi. So we have critical points at 4 places, 2 pi and 0 being identical. So let's go ahead and graph this. We've got our value of t, x, and y. Let's go ahead and use those intervals there. Alright, so at 0 we have 5, 0, pi over 2, 0, 5. We actually had something like this in the last section. Negative 5, 0, 0, negative 5, and back at 5, 0 as we were at 0. So, if we graph this, what we get, and I'm not going to do it justice, I'm sure, is we are going to have a circle. We have a circle where we have a slope that is 0 at pi over 2. Okay. We have a slope that's 0 at 3 pi over 2, undefined at 0, and at pi. So we do, in fact, have critical points at all of those places. All right, and those points are given here in our chart. Okay, so cosine and sine actually uniquely define some circles. In this particular, it has a radius of 5. So there we have it, going in the counterclockwise direction. Number 2, find the equation of the tangent line to the curve defined by these equations, and specifically we're given down here when t equals 2. Right, so the equation of the tangent line is going to be the same as it always has been. First, we need to find our derivative. Following the same pattern here, the derivative of y is 2. Derivative of x is 2t, so our slope function in terms of t is 1 over t. So the slope of this line is going to be dy dx evaluated at t equals 2, which would make our slope 1/2. Now what is our point at t equals 2? Well, our point with t equals 2 is going to be 1, comma, plugging in 1 there, we get... That can't be right. Nope, that's a 3. There we go. So 1, 3. I plugged in 1 there. Okay, so we have the point 1, 3 and a slope of 1/2. So y minus y1 equals mx minus x1. Use our point slope form there. All right, 1/2 times x minus 1. Distributing there, 1/2 x minus 1/2. Which means y equals 1/2 x plus 2.5, so 5 over 2. And there is the equation of our tangent line with this curve. All right, example 3. Calculate the second derivative. Now, this is actually using the same function. I'm going to go ahead and write an equation that is quite important for finding the second derivative. So d squared y over dx squared is equal to d dx of dy dx. Now that is just the standard definition. But the way we're going to write this is a little different. This is d dt of dy dx divided by dx dt. So we'll take the derivative of, and if you notice, we basically added in a dt there, the differential. You can sort of think of it that way. Again, that's not exactly what's happening, but that's pretty close. We effectively added in a dt down here. Instead of a d dx, we have a d dx and a dt. We're taking the derivative with respect to t because dy dx is going to be in terms of t. Okay, we have some crazy things happen without doing that. All right, so from the last question, we know that dy dx is 1 over t. So d squared y dx squared is going to be d dt of 1 over t, derivative of that with respect to t, divided by dx dt, which we know dx dt is just 2t. And the derivative of 1 over t is negative 1 over t squared. And so our second derivative is negative 1/2, but we are going to have a t cubed there. Okay, there is a formula for our second derivative. All right, the next application we're going to tackle is area under a parametric curve. This formula is very similar to the area under a curve. In general, we have y of t times x prime of t dt. That is our formula if we have those two. So let's go ahead and find the area under the curve of the cycloid defined by these equations. So our area is going to be equal to the integral from 0 to 2 pi of y, that's 1 minus cosine t, times x prime, which is 1 minus cosine t dt. All right. First, I'm going to multiply this out. That'll be 1 minus 2 cosine t plus cosine squared t dt. Now going back to our section on trigonometric integrals, we have this identity where cosine squared t is 1 plus, or I'll write it differently, it is 1/2 plus cosine 2t over 2. Bring down the rest of this. 1 dt integral from 0 to 2 pi. Combining like terms there, we have 3 over 2 minus 2 cosine t plus 1/2, or I'll leave that over 4. Cosine 2t over t over 2 dt. Okay, now we can take the antiderivative. 3 over 2t minus 2 sine t plus sine 2t over 4, evaluated from 0 to 2 pi. And I'll save you that work there. For that, we are going to get 3 pi. So the area underneath that cycloid is 3 pi. All right, the next thing we'll tackle is arc length. We'll move from arc length then to surface areas, and that'll be the end of our applications. But this should look fairly familiar. The arc length formula in terms of x is 1 plus dy dx squared. So instead of that, we have x prime squared plus y prime squared. It actually derives the same way as it did as a Riemann sum in previous chapters, so worth just glancing back at that. So we're going to take these two functions and find the arc length of this semicircle. So our length equals the integral from 0 to pi of the square root of x prime squared. Well, x prime is going to be negative 3. Let's write that again. Negative 3 sine t. And the derivative of this is 3 cosine t. We're going to square both of those. Okay. Well, squaring that, we get 9 sine squared t plus 9 cosine squared t. Hopefully you notice we can factor the 9 out, so this is actually 3. I could factor it out of the integral as well. 3 square root of sine squared t plus cosine squared t. Now the Pythagorean identity tells me that is actually equal to 1. So when I take the antiderivative of, so this is times 1 here, the antiderivative of that is 3t, evaluated from 0 to pi, which will be 3 pi. Different functions, same answer, but this one is arc length, and the other was area. Quite a difference. All right, for a surface area, I wrote both these formulas here. I want you to sort of compare these two. The original one we had in the previous section was 2 pi, and I think there should actually be a 2 pi in that one as well. Add that in there. All right. The original function was 2 pi, the integral of f of x times the square root of 1 plus f prime of x squared. That is the y value times the arc length. Well, that's exactly what we're looking at here, just that our arc length formula is different. So let's go ahead and find the surface area of a sphere of radius r centered at the origin. All right, so our surface area, S, and we are using this formula because we have parametric equations. And actually, we don't have any equations. So let's go ahead and write something down here. This is a sphere centered at the origin of radius r. So our x value is given by r cosine t, as we've seen previously, and our y value is r sine t. And in this case, because it's the surface area, we actually want to go from 0 to pi. That is, we're taking this half circle and rotating it to find the surface area. So our functions then are going to be given by that. So we'll say 2 pi from 0 to pi of the square root of the derivative of x. And actually, let's add in the original function, y of t, so r sine of t. And the derivative of x is negative r sine t squared. Derivative there is r cosine t squared dt. All right, messing with that a bit. That is going to be r squared. Okay, let's go ahead and write that in there. So r sine t, r squared sine squared t, plus r squared cosine squared t. Now, the r squared can be factored out. So we're going to have an r squared out here. Sine squared t plus cosine squared t. Integral 0 to pi 2 pi. This term is 1. Again, Pythagorean identity. So we have r squared, which is actually a constant, does not have a value of t in it. So this is 2 pi r squared integral from 0 to pi of sine of t, which is going to be negative cosine t, valued from 0 to pi, which is the value of pi there of cosine is negative 1, so that will be 1, minus evaluating that at 0, that is, did I say that right? Negative 1, so that would be positive 1, yes, okay. 0 would then be 1, so that is minus 1. Okay, so that would be plus 2 pi r squared, which is 4 pi r squared, which is exactly the surface area formula that we are familiar with. So we can actually derive some formulas based on these parametric equations. All right, that brings us to the end of this section of this calculus. This is a very quick overview of calculus in this new mindset. All right, so you might go back, and there are lots of other things in the textbook that you can kind of see that are not worked out problems, but there are some things where they prove some things that will be very useful.